Hello guys. Today in this video we are discussing more about this metal semiconductor junction or Schottky diode that we discussed in the previous video. So today in this particular video we are going to talk about metal semiconductor contacts. So if you remember in the previous video we discussed about this metal semiconductor junction, and we discussed about different types of biasing, starting from zero bias and reverse bias, forward bias, all those we discussed. Okay, so basically, if you remember, in zero bias, we got the current is zero, and in forward bias, we got I equals I naught exponential e to the power E VA applied voltage divided by KT minus 1. This was the current value for forward bias, and for reverse bias, this was for forward bias. And for reverse bias, we got I equals I naught e to the power minus EVR, the reverse voltage, KT minus 1. Okay, and we define this I0 as E R T square e to the power minus E phi Bn over KT. This is your I0 value. And this R here we wrote is the Richardson constant, which was defined as 4 pi E mn star effective mass of the electron K square divided by HQ. For detail, you can revisit the previous video, that is Richardson constant, this R whole thing we defined. So this is what we have discussed. So now if you plot this, okay, and we'll plot the voltage versus or IV characteristic for this Schottky diode, then we can just simply show the characteristics. So if I have this voltage axis and current axis, then for the forward bias, we will get a graph like this. Okay, so this indicates the IV characteristic when the metal semiconductor junction diode is in forward bias. Similarly, the other one you will see the continuity. You can see it goes like this and this. So this is for reverse bias. Okay, so these are the things that we discussed. Okay, now in this video we are going to um, discuss more about metal semiconductor contacts. Okay, so if we'll discuss metal semiconductor contacts, metal semiconductor contacts, then we can actually classify into two types. One is ohmic, or we call it non-rectifying, non-rectifying contact. And the other one, we will say Schottky or rectifying contact. Okay. Further, this ohmic or non-rectifying contact can be classified into two types. Okay. One we will say ideal non-rectifying contact, ideal non-rectifying contact, and the other one is tunneling barrier. Okay. So this metal semiconductor contact can be actually classified or can be understood this way. So first we said ohmic or non-rectifying, the other one is not pure rectifying. Further, ohmic or non-rectifying can be classified into ideal, non-rectifying, and tunneling. Okay. So let us try to understand more about this ohmic contact. Okay, what is the ohmic contact between metal and semiconductor? Okay. So if you write what is ohmic contact, basically ohmic contact is a low resistance junction, providing conduction in both directions between the metal and the semiconductor. Okay, so this ohmic contact we will say as for low resistance junction, providing conduction in both directions, metal to semiconductor and semiconductor to metal. Between the metal and the semiconductor. Let us try to understand this using the time diagrams. Okay. So this is what is ohmic contact. Ohmic contact means a low resistance junction between this metal and semiconductor. So let us first discuss about ideal non-rectifying or this ohmic barrier. Okay. Ideal non-rectifying or which is ohmic barrier that we will discuss first. Fine. So if you will draw the metal semiconductor band diagram, we have to start with a vacuum level. This is our reference for the vacuum level, right? This is the interface between the metal and the semiconductor, N-type semiconductor, and here we have this side is metal. Okay. Then the conduction band, the N-type. Okay. Chi, the electron affinity. Fermi energy level of the N-type close to the conduction band. Fermi energy level to the vacuum level is our semiconductor work function. Then we have the valence band of the semiconductor. And the Fermi energy level of the metal, we defined here Fermi energy level of the metal. So the metal work function, we can write E phi m. This is the Fermi energy level of the metal. The condition here that we have taken, the type of semiconductor we have taken is N type. And the condition is phi m, the metal work function of the work function is less than the semiconductor work function. This is what the type of metal and semiconductor contact that we have taken. Okay. So here we are discussing ideal, non-rectifying, or ohmic. Ideal, non-rectifying. Okay. Now here, as you can see, first thing is to achieve thermal equilibrium in this junction, right? So to achieve thermal equilibrium in this junction, what will happen? The EFM and EFS in both the sides, okay, have to be constant throughout. So let us redraw this for vacuum level, the interface junction here. Then EFM and EFS should be constant in thermal equilibrium. So here this side we have EFM and this side it is EFS. And to make this constant, as you can see, there will be bending observed. You can see at the conduction band. So EFS semiconductor side forbidden energy level is moving up, right, to match with this EFM. So you can see there is a bending in the conduction band. Okay, when the original gap was this was the original gap. You can see EC and EF, between EC and EF, right? So we can see that it will bend, it will go like this from here, and then you got your conduction band, right? Similarly, the same thing will happen with the valence band. It will go up by the same amount and will go like this, EV. So this side is our N type, and this is your metal side. So after the contact, this is what will be observed, right? The form energy level will be constant throughout the conduction band and valence band. You can see bending, and you can see the barrier that is created over here. Okay. So to achieve thermal equilibrium in this particular junction, electrons, okay, from the metal into the lower energy states in the semiconductor, they will move, right, which makes the surface of the semiconductor more n-type. So if you see in this case, so now you can see electrons will flow from the metal side. You can see the energy level of the metal is at a higher position, the firm energy level of the metal. So the electrons will move from that metal side to the lower energy states available in the semiconductor. And this makes the surface of the semiconductor more n-type because of more number of electrons moving from the metal side to the semiconductor side. Okay, if you will give a positive voltage, okay, a positive voltage applied to the metal side. So, for example, here if you will give a positive voltage to the metal side, okay, and ultimately this is negative. Negative is connected to the N type. This is positive. This is negative. There is no barrier to the electrons that is flowing from the semiconductor to the metal. You can see that. So from the semiconductor to the metal side, there is no barrier. Okay. So if a positive voltage is applied to the semiconductor, this side we will give a positive voltage. Okay. The effective barrier height for electrons, the effective barrier height that we got here, okay, for electrons flowing from the metal into the semiconductor will be very, very small. Okay. For this bias condition, electrons can easily flow from the metal into the semiconductor, as you can see. So the barrier height in both the cases, like from the metal to the semiconductor, you can see the barrier height is small. And from the semiconductor side to the metal side, also it is small. So let us draw. I mean, I will show you two better diagrams to understand this. Here we just try to see the position of the Fermi energy level, and when there is a contact, what happens to the bending, and the Fermi energy level in equilibrium will be constant throughout. So now let us see the biasing thing when I will give positive or negative to the metal or the semiconductor side, what will happen. So let us draw a simple diagram. So this is our Fermi energy level of the metal side, EFM, and we are connecting it to the positive. Okay. And this is our N-type semiconductor side. Okay. Now here, what will happen? We said, this is what is the structure of the conduction band now. Okay. Because the interface here will become more negative as the Fermi energy level of the metal was at a higher position and more number of electrons are moving, okay, at the junction, making it more negative. And this kind of similar band bending will be observed in the valence band. Okay. So now for the electrons that are here, okay, in the conduction band, they are kind of moving downhill and not appearing any potential barrier. So this is kind of easy for them to move from the conduction band of the semiconductor side to the metal side. So positive voltage applied to the metal, electrons can easily flow downhill here, okay, from the semiconductor to the metal. Similarly, for the other case, if you will connect the metal to the negative terminal, okay, this is our metal side. and this is our N type. So here you will see a kind of the variation of the bands will be like this, just the opposite. The bias is now exactly opposite, right? So here we connected this to the negative terminal and this to the positive terminal. Okay, making this N type more, here positive. Okay, but here it is little negative. So in this case, you can see that the electrons that are present in the metal side, okay, the barrier height is kind of less here. So the electrons can easily flow from metal to the semiconductor side. You can see that. Okay. So this is how, if a positive voltage is applied to the semiconductor, we said positive voltage is applied to the semiconductor, the effective barrier height for electrons flowing from metal to the semiconductor will be small here. Okay. And in this particular bias condition, electron can easily flow right from the metal to the semiconductor. So both way you can see. In one case, electrons can easily flow from N type to the metal. In the other case, the electrons can easily flow from the metal to the N type semiconductor. Okay. Similarly, we can do it for P type where phi m is greater than phi s, that is metal work function is greater than the semiconductor work function. I will just draw the band diagrams and you can easily interpret yourself. So for P type, suppose we are taking a P type semiconductor connected or like forming a contact with the metal. Okay, then what will happen? Phi m is greater than phi s will be considered. Similarly, exactly the same way we will do before contact. We got this EFM, and suppose this is the side is the metal side. We have a conduction band. The Fermi energy level now is closer to your valence band. So suppose this is your valence band, and the Fermi energy level of the metal we have considered is greater. Right, suppose somewhere here we can consider this EFM. So you can check the metal work function E phi m, okay, is greater than the semiconductor work function, which is E phi s. Okay, now when we will make a contact between them, then you can see what will happen. The EFM and EFS will now be constant in thermal equilibrium. EFS, and this is your EFM, right? Then you can see the position of the EFS is at a higher position, from energy level is at a of the metal side is at a like no lower to that EFS. You can see. So EFM will move up, or you can say EFS will go down. So this way you can see that the conduction band here will be shifted downward, like this is EC, and this one the valence band will also bend accordingly and will go down like this. So EC, right? This is our P type here we considered, and this is the metal, right? And here you can see for the holes, if the here, this is the barrier height, okay? And accordingly, you can see the bias and what will happen, right? So this is for P type, phi m greater than phi s, whatever, what will be the uh, band structure and what are the barrier height from both the side, metal to the semiconductor or semiconductor to the metal. When P type is connected to the majority charge carrier is hole here, right? Okay. So now let us discuss more about this tunneling barrier. Okay, we said tunneling barrier is also one kind of ohmic or non-rectifying contact and tunneling barrier we will see. So here we will use the space charge width in a rectifying metal semiconductor contact. Okay, so for that we can write the expression that we are aware of already, we have derived. You can refer to the previous videos where we have already discussed this. W, the space charge width, okay, in a metal semiconductor junction can be written as twice epsilon s ER plus VBI. VBI is the built-in potential barrier, reverse bias voltage VR, divided by E and D, and D is the doping concentration. N-type semiconductor, it is evident as we are writing ND, epsilon s is the semiconductor permittivity. Okay, so this is given as the space charge width. So the space charge width of a rectifying metal semiconductor, we are talking about rectifying metal semiconductor contact, is inversely proportional to the square root of the semiconductor doping that is visible. Here you can see ND is the doping concentration to the power 1 by 2 it is, right? So that's what is observed here. Width of the depletion region decreases as the doping concentration increases. So if you increase the doping concentration, the width of the depletion region will decrease. Okay, and the electrons here can tunnel across the barrier, across the barrier. That's the reason we call this phenomena as tunneling barrier. Okay, so W is equal to Xn, and we have the expression from this. So now here, if we draw the band diagram, it seems like the semiconductor junction we got, and this is our EFM, Fermi energy level, both the side, EFM after contact I'm showing you, EFS, right? Here you will see that there is a structure like this. Okay, same kind of bending you will see here. In the metal semiconductor junction, right? The barrier height, you can see this is the barrier height, which is E phi Bn, right? Now, in this case, electrons can easily tunnel through from the metal side to the semiconductor side through the barrier, and similarly from the semiconductor side to the metal side like this. Okay, so the electron can easily tunnel through this. Okay, so here how it is formed, you can see there is a epitaxial layer basically. So here the metal is in contact with a heavily doped. How it is created, this part you can see the EC, the conduction band here is very close to the Fermi energy level in this particular region, right? So that gives you N-type, doped N-type epitaxial layer, we call it. So it is a heavily doped N-type epitaxial layer. Okay, so it is designed knowingly so that the tunneling can happen easily. The electrons can move from the semiconductor side to the metal side and metal side to the semiconductor side. Okay, so this is what is the structure. Heavily doped N-type epitaxial layer. You can see that is evident from the band diagram. This region where conduction band is close to the Fermi energy level, here in this region more close to this. Okay, so forming that epitaxial layer that helps the electrons to move from both the sides, metal to the semiconductor side. Okay, so this is how the tunneling happens. Okay, now the tunneling current, the expression I'm writing, the derivation we will do in some other video. Here the tunneling current, the expression for the tunneling, if you write, the expression is given as the current density is directly proportional to minus E phi Bn, barrier height from the metal to the semiconductor side, divided by E0. Okay, where E0 is actually EH bar by 2 square root of the doping concentration epsilon s, semiconductor permittivity, and Mn star effective mass of the electron. Okay, so this is the expression for the tunneling current. Okay, we will discuss about this, the derivation of this tunneling current in some other class. Okay, there is one more thing we should know, which is known as the specific contact resistance. So, what is that specific contact resistance? That we will just define the formula for this. So, basically, the specific contact resistance is defined as the current density del G upon del V inverse, and the applied voltage is 0. The unit we can write as centimeter square. Okay, so using this. So the expression for J, the current density we said, current per unit area, is given by RT square exponential minus E phi Bn divided by KT. If you remember, we wrote about I0. Okay, now exponential of EVA by KT minus 1. This was the expression. You will substitute this del J here, and you will take the del J by del V, right? And then inverse of that, substituting VA is 0, then we will get RC as KT by E exponential e to the power E phi Bn by KT whole divided by RT squared. Okay. So here in this expression, you can see the specific contact resistance RC decreases, okay, faster as the barrier height increases exponentially, you can see, right? So e to the power minus E phi Bn by KT, and then exponential of EVA by KT multiplied with E by KT if you take the derivative, okay, to the power minus 1. So specific contact resistance decreases rapidly as the barrier height decreases. Okay, so they are directly proportional. You can see exponential, but it is, sorry, not directly proportional. It's e to the power E phi Bn by KT, so exponential. Okay, so for a metal semiconductor junction with a high impurity concentration, doping concentration, that is the value of Nd, the tunneling process will dominate. Okay, so if the metal semiconductor junction has a very highly doped semiconductor, then the tunneling process will dominate, and we got that RC is proportional to e to the power 2 square root of epsilon s, the E0 value that we use there. So it will substitute epsilon s Mn star divided by H bar multiplied with pi Bn divided by square root of Nd. Okay, so this is what RC depends on. So we got the relationship between the specific resistance and the barrier height. Okay, and also we got the relationship between the specific resistance and the doping concentration in the semiconductor side. Okay, so this particularly shows that the specific contact resistance is actually a very strong function of the doping concentration. So by varying the doping concentration, we can change the specific contact resistance. As a result, the current density can also be changed. Okay. Thank you for watching.